Yeah.
I started the.
Okay.
Okay. I think we have accumulation about over 100 participants. So I think for time issues, I think we have to go ahead with the event. So welcome everybody. This is Dr. Mohammed Ahmed from the IRC Interdisciplinary Research Center for Hydrogen and Energy Storage, headed by Professor Zaini Amani. And energized, as a matter of fact, with the first class researcher and affiliates to the center. Tonight, inshallah, we have this very important event on hydrogen economy, status and ambitions. And as a matter of fact, we are highly motivated behind this event with so many issues related to the hydrogen in terms of hydrogen production, clean hydrogen production for green hydrogen and the blue hydrogen, also the hydrogen engineering process in terms of hydrogen transportation and the storage, as well as utilization in the different system for power production. As a matter of fact, clean hydrogen, as an overview, clean hydrogen technologies in terms of blue or green hydrogen are already available and well evaluated, but as a matter of fact, the cost is remaining still as a challenge. And this is the subject of this event. But as a matter of fact, by scaling supply chain and investing more in this direction, we can reduce, as a matter of fact, this cost down. Saudi Arabia here is exploring, as a matter of fact, its way to become the top supplier of the hydrogen in the world, as a matter of fact, for decades supplying and securing the energy for the world. And Saudi Arabia has, as a matter of fact, a clean hydrogen production target of about 3 million tons per year by the year 2030. The current focus in Saudi Arabia is to gain large market, as a matter of fact, share in the blue hydrogen, particularly in the form of blue ammonia in the coming decade. But that does not mean by any means that Saudi Arabia does not pay the right attention, as a matter of fact, to the green hydrogen as well. Of course, it does. We have hydrogen from renewable energy sources, or what's called, as a matter of fact, green hydrogen, could mean a new industrial sector in Saudi Arabia, because Saudi Arabia, as a matter of fact, is enjoying one of the lowest price of green energy production in the world. And this can be reflected, as a matter of fact, on the cost also of green hydrogen. Saudi Arabia can have a great market share in this direction as well. Also, we have the city of Neom, as a matter of fact, is a clear example about this direction of green hydrogen, and it is expected to play a central role in Saudi Arabia interest in ushering in green hydrogen supply. Motivated, as a matter of fact, by all of this, KFUBM with the new administration, with a new ambitious plan to become a research-intensive university, under the leadership of His Excellency Dr. Mohammed Ahmed, and with the care and continuous support from His Royal Highness Prince Abdulaziz bin Salman. So we have here at KFUBM a number of research center has been established of interdisciplinary nature. One of them is a dedicated center for hydrogen and energy storage. So we are here tonight. We have this very interesting forum. We have very special speaker tonight. Inshallah, will be talking to us about hydrogen economy, and we'll discuss the current advancement and ambitions. Tonight we have, will be just very brief. We have Mr. Wolfgang Brand, he is Air Product Vice President, NEOM for green hydrogen. He will be talking to us tonight, inshallah, about the global status of hydrogen production and the transportation. We have as well Dr. Mazen Zarif, he is advisor at the Ministry of Energy, and he will give us, inshallah, talk about the Kingdom vision and ambitions regarding the hydrogen economy. We have very special guest tonight. Also, we have Professor Omar Yaghi. He is a professor at the University of California, Berkeley. And Professor Yaghi, as a matter of fact, he has been shortlisted for the Nobel Prize. And very soon, inshallah, he will hold this prize. Professor Yaghi tonight, inshallah, will be speaking to us about the recent development in hydrogen storage material. Last but not least, for sure, we have Dr. Mohammed Ahmed. He's assistant professor at KFUBM, and he will be speaking to us, inshallah, talk about the challenges in setting socio-economic models for the hydrogen economy. Tonight, inshallah, we have a plan to start with Mr. Wolfgang Brand to give us his talk. So, Mr. Brand, are you available? So I think he have IT issues, so it will be resolved, inshallah, very soon. So we can start, inshallah, with Dr. Mazen Zarif. Dr. Mazen will give us, inshallah, a talk about the Kingdom vision and ambitions regarding the hydrogen economy. Dr. Mazen has joined the Ministry of Energy in 2020, and he has a career spans over more than 22 years in the energy sector. He previously worked in leading companies, multinational companies like Baker Hughes and General Electric. Dr. Mazen, mashallah, has a degree in mechanical engineering from King Fahd University of Petroleum and Minerals. So he is the son of KFUBM, and he has MBA from the University of Manchester. Dr. Mazen, the floor is yours, inshallah, for 25 minutes, followed by 5 minutes for question and answer. For audience, please just write down your question and answer, and inshallah, we'll be just responding to them within the time slot for Q&A. Dr. Mazen, please, the floor is yours.
Thank you very much, Dr. Mohammed. Let me start first by sharing my screen. Okay. So, do you see my screen? Okay, please let me know when you start seeing my screen. Okay. So do you still hear me? Okay, perfect. Then I'll get started. So first of all, thank you, Dr. Mohammed, and thanks to KFUPM, and thanks to the Center of Hydrogen and Energy Storage Research for giving me this opportunity. It's a pleasure to be here. By the way, I'm not a doctor, although Dr. Mohammed is introducing me as a doctor, but I guess this is the privilege of being surrounded by doctors and professors. So I'm actually a graduate of KFUPM, so it's always a pleasure to be back and present here with the KFUPM team. I graduated in 1999, so it's been quite a while, as you can see. So without any further ado, let me get started with today's presentation. And I'll be talking about KSA's vision and ambition regarding the hydrogen economy. So I'm going to be sharing with you the following agenda. So first, an overview of KSA's hydrogen vision. And then after that, we're going to move to the second section of the presentation, which is going to be the current challenges faced by the hydrogen industry. And then the third section, which is going to be the suggested areas for collaboration in R&D and innovation. So actually hydrogen is versatile and potentially emissions-free. However, its adoption at scale has several challenges. Now on the left, you can see different hydrogen production methods. And the first two on the top is using the coal gasification, and the second one, which is using the natural gas reforming. Now, these production methods are associated with CO2 and very significant CO2 emissions. So they're not clean hydrogen as far as GHG emissions. However, hydrogen can be produced using clean methods. So we consider, normally they're referred to in color codes: black, gray, blue, green, and normally the green and the blue are the ones associated with no emissions or very low carbons. But however, we refer to them as clean hydrogen. For example, if you talk about the use of the SMR, steam methane reforming, and other forms of producing hydrogen from the natural gas, if the CO2 is captured, that prevents the CO2 from being emitted to the atmosphere. So that's a clean production method. In addition to the use of the electrolysis, which is powered by renewable energy. So there is no emissions to begin with in that production. And for our strategy for the clean hydrogen production, we'll be focusing on those two clean production methods. Now, the advantages of hydrogen would include that it's emissions-free, and it has a high energy per mass. And it is, as we mentioned, it's very versatile. So it can be used as a fuel, it can be used as a feedstock, it can transport energy, and it can store energy. However, there are associated challenges with hydrogen, issues with the transportation. So for example, here in Saudi, it's relatively cheap for us to produce hydrogen. However, it's expensive to store and to transport. There are also less developed markets for hydrogen globally. And a big issue actually, which is the fragmented certification for hydrogen. So whether you produce clean hydrogen or hydrogen with a CO2 associated, hydrogen cannot speak on its own. So you have to have the certificate that says that there is no CO2 associated with that. Now, let's take a quick look about what's going on globally for hydrogen. So globally, clean hydrogen is expected to grow into important energy vector and as an industrial feedstock. However, wide variance exists on the demand. And you can see the forecast of hydrogen here on hydrogen demand. There is variance, especially as you look on the longer time horizon. If we just take a look at the estimates by the Hydrogen Council, so by year 2030, it's expected that demand is going to be around 60 million tons per year of clean hydrogen. And by 2040, it is expected to be around 250. Now, the consensus amongst all these forecasts that there is a growth in demand for clean hydrogen. Now, in this context, Saudi Arabia is well positioned to be or to play a leading role and become a major clean hydrogen exporter. So you'll see that different regions within Saudi are suitable for clean hydrogen production. The western, especially the northwest of Saudi Arabia, where it can produce hydrogen based on the electrolysis process that is powered by the solar and wind. The solar and wind and the renewable energy conditions in general are very favorable in these regions. Now, if you take a look at the eastern side of Saudi Arabia, where there are abundance of hydrocarbon resources, but in addition to that, the capabilities to store or to sequester the CO2 emissions once captured. So this gives us the capability to both be able to generate hydrogen that is based on electrolysis powered by the renewables with no emissions, or to produce hydrogen that is based on SMR, steam methane reforming, or thermal reforming with the natural gas, but with the CO2 capture and then the CO2 sequestrations and therefore minimizing the CO2 emissions. So in Saudi, we do have the advantage of both of these options. In addition to that, Saudi has an existing infrastructure to globally export hydrogen in its location. As we can see, there are actually demand centers will be in Europe and Asia, and Saudi is in a position where that it can support both these regions, in addition to the financing advantages. So KSA's strategic advantages make it well positioned to be amongst the lowest producers of clean hydrogen and has an adequate land to produce and to scale up these volumes as we go. Now, from production point of view, Saudi has the potential to achieve one of the lowest cost of clean hydrogen globally. And the bar charts that we see on the left shows the production cost, and we've just indexed that to 100, because the costs will vary in different ranges. However, if we just index that to 100 for gray hydrogen, then if you compare that to blue hydrogen, which will be using the steam methane reforming or autothermal reforming, but with the carbon capture on top of that, so there will be an additional cost, of course. So as you can see, it's a little bit more than the gray cost. And then the green cost, which is significantly more than the blue hydrogen cost. Now, having said this, looking at the 2030 time horizon, the cost for both blue and green hydrogen is expected to reduce. As a matter of fact, they will both reach parity around the time horizon of 2030. So this will give an advantage for the electrolysis-based production or the green hydrogen to expand more, but beyond the 2030 time horizon. However, for the current time horizon, the SMR-based hydrogen has a clear cost advantage. Now, if you look at these two options for the time being, specifically for Saudi has a lower levelized energy costs globally. However, the reduction that you see here is a result of the reduction of the capex for the electrolyzers. So the cost of the electrolyzers, and if you compare the cost of where it is right now towards what it's going to be in 2030, is expected to reduce significantly, almost by half. And on the other hand, there will be also some price reduction for the blue, and mainly it's a result of the reduction of capex for the carbon capture facilities, or the capex out of the carbon capture requirement. And also there will be better integration with CCS hubs and better handling, the cost will also reduce further. Now, KSA's strategic advantage for clean hydrogen production will allow it to compete for the key target import markets. Now, looking at this global map, we can see that in Saudi, we're positioned between the some of the important regions in the world and countries. So the ones that are highlighted in dark brown, mainly you see that it's the European Union countries, in addition to the Far East, specifically South Korea and Japan. These would be importing countries. Now, there would be other countries, if you think about what's going on with North America. To a large extent, it's going to be self-sufficient, so they will be producing and they'll be consuming most likely all the hydrogen production. China is expected to be self-sufficient as well when it comes to hydrogen. Exporting countries will include, of course, Saudi Arabia and some GCC countries, in addition to North Africa and Chile and Australia. Now, KSA will leverage this competitive edge to gain a first mover advantage, aiming to become a leading exporter of clean hydrogen at global scale across key importing markets. Now we have developed the national hydrogen strategy, focusing on production, exports, and also domestic use of clean hydrogen. Just a quick recap here on the production methods. So we can produce hydrogen using renewable energy, which will power the electrolyzers. And then as a result of that, we can get the hydrogen, and we classify that normally as green hydrogen. Another method that we've highlighted also is the use of natural gas, and then through a process, for example, the steam methane reforming, where we can produce hydrogen. However, the CO2, instead of venting it to the atmosphere as what happens in gray hydrogen, the CO2 is captured, and this makes it clean hydrogen as well. Now, in addition to the production of hydrogen, we can produce hydrogen derivatives, such as ammonia, which is NH3, and some other types of syn fuels when you combine hydrogen with the CO2 captured. Now, what do we do with all these hydrogen produced and the derivatives? Our strategy is to utilize them. Part of that is going to be used for local or domestic use cases. And part of that also will be used to generate hydrogen derivatives and hydrogen products. These products can be used for oil refining or for ammonia fertilizers. They can be used as aviation fuel or low carbon steel. The majority of the clean hydrogen production is expected to be exported to the demand centers around the world by the countries in Europe and Japan and South Korea. Now we've actually started the implementation phase, and we're focusing on 5 priority actions. First, conducting government-to-government engagements to secure partnerships in the hydrogen ecosystem. For example, securing offtake agreements and working on R&D partnerships. And we have, like, for example, we also have an MOU or a memorandum of understanding signed with Germany on collaboration on hydrogen. We're also focusing on supporting hydrogen mobility pilots, such as use of hydrogen in buses, taxis, rail, and we'll get into the details of that, where the Ministry of Energy has signed MOUs with 8 entities in Saudi Arabia to pilot mobility applications. We're also focusing on exploring the feasibility study for hydrogen transportation infrastructure. For example, a pipeline and from KSA to the importing countries. In addition to that, another important topic is establishing regulatory framework for hydrogen, such as standards, certifications, and advocating for global harmonization of standards. And then we're also focusing on developing enablers to expedite hydrogen-related investments and FCEVs adoption. So recently, 8 entities, along with the Ministry of Energy, declared a commitment by developing hydrogen mobility pilots. This was signed end of January, where the ministry, His Royal Highness the Minister of Energy, signed with 8 entities. These entities included the piloting the FCEVs in college campus community with Princess Noor University, and hydrogen train using 1 or 2 of the routes of SAR, which is the railway company, and also the syn fuel production with Taqniya, but also it included the Royal Commission for Mecca City and Holy Sites for piloting buses, and also the Saudi ground services for airport ground handling using hydrogen and FCEVs, in addition to NEOM and the Red Sea Development Company and the Royal Commission for Jubail and Yanbu. All these entities will be piloting FCEV and the use of hydrogen in mobility. Okay, moving on to the next section, we're going to talk about the current challenges faced by hydrogen industry development. So despite momentum across hydrogen demand and supply, four challenges still face the scaling of hydrogen into global energy. So the demand and use cases, potential uncertainty regarding the speed and scale of investments following demand announcements, and also the hydrogen heavy-duty mobility, ammonia to be competitive by 2030. And there are, of course, other challenges in production, such as higher production costs of clean hydrogen, current conventional alternatives, and in addition to the transportation of hydrogen, where we can use current, where we have challenges such as the current transportation options are expensive. So whether you consider the how capex intensive it is to build a pipeline to, let's say, important regions such as Europe, so that's a big challenge. But also even a more practical way of doing it as of now, such as converting hydrogen into ammonia, for example, will also be capex intensive, and as it requires building the right infrastructures by converting facilities from hydrogen to ammonia at the exporting countries, and then reconverting it back to hydrogen at the importing countries. And last but not least, the market certifications. So as I mentioned, hydrogen does not speak on itself to say I'm low carbon or I'm clean. So that is only achieved by certifications. Now the global certification efforts around the world is scattered, and it has a limited visibility on the evolution of certifications. Okay, moving to the last section, which is suggested areas of R&D and demo collaborations. So a list of actually good research and development initiatives have been identified based on these prevailing topics and relevance across the value chain. So if you look at the production part of the value chain, we talk about that there could be good initiatives on the electrolyzers and the use also of wastewater and seawater in electrolyzer. So as of now, for example, alkaline-based electrolyzers, they use fresh water. Now, if we want to look at the scarcity of water in Saudi Arabia, it would be a good research topic to focus on the use of wastewater and seawater for these electrolyzers, as they're both going to be like carbon neutral, but also this will prevent us from using fresh water for producing hydrogen and better use of these alternatives. In addition to that, electricity storage, which is an important part, and then the carbon capture, transportation and storage. Another research topics related to production is the direct oil to hydrogen, or the use of or producing basically hydrogen from oil rather than natural gas, because there's abundance of oil in Saudi, and also the plastic waste to hydrogen. On the transportation fronts, there are several topics such as the liquefaction of hydrogen, transport of liquid hydrogen, and the reconversion of ammonia to hydrogen. In addition to the pipeline retrofitting, there are large and existing pipeline network, maybe mainly for natural gas. So retrofitting does save a lot of capex. And then on the end use cases, the use of hydrogen in the DRI or the steel production, and also the use of hydrogen in the hydrogen-based fuels such as e-methanol, e-kerosene, etc. And of course, the fuel cell technologies and so forth. Now we have assessed and prioritized the prevailing research and development topics based on basis of A, the strategic advantages to Saudi, and B, the criticality of development for this technology. So mapping all these different technologies and whatever ranks very high on the strategic advantage to Saudi and ranks also to criticality of development would be the #1 priority. And then moving to other priorities, #2 and #3, that would rank lower in the strategic advantage and the criticality of development. This helps us to decide on what is going to be to give us a top priority. So if you just take, for example, as direct oil to hydrogen production, as an example. It is going to be enabling us to produce hydrogen from oil, and how strategically important that is to Saudi because of the abundance of oil reserve or oil access in Saudi. So that ranks very high. And then you can look at these other technologies that can form also good areas for innovation and R&D topics.
Mr. Mazen, please, we 1 and 2 minutes, so please.
Absolutely. So this is, I believe, is the last slide. So KFUPM and other research institutions could take the lead in developing the priority for the research and development areas, maximizing Saudi clean hydrogen competitive advantage in international markets, and better utilize for Saudi Arabian resources for the long-term socioeconomic development, and also be at the forefront of the clean hydrogen economy by developing Saudi Arabian capabilities and intellectual property. I think with that, I reached towards the end. So thank you very much for giving the time and for listening. And back to you, Dr. Mohammed.
Thanks, Dr. Mazen, for the very interesting presentation, and thanks for joining us tonight. So we'll go directly, as we have a tight schedule tonight, we will go to select a number of questions from maybe a couple of questions or something from Q&A. We have here one question from Mr. Ahmed Belfas. He have a question to you. He is asking, what makes the cost of green hydrogen storage in Saudi Arabia very high comparing to other countries?
What makes the cost of hydrogen production high?
The cost of green hydrogen storage in Saudi Arabia very high comparing to other countries.
So for storage of, once hydrogen is produced, it doesn't matter if it's green or any form. Once hydrogen is produced, it is hydrogen. It doesn't matter. Once you produce hydrogen, you're going to become color agnostic on what happens next. Now, why is hydrogen expensive to both transport and to ship? If you just think about it, if you want to, for example, to store it, in order to store a lot of hydrogen, the best way maybe you think of it is to convert it from its gaseous state to liquefy it, which will be very energy intensive. So that will be very costly, and then you have to keep it at, I think, minus 250 or something really, really cold to keep it in its liquid state. So that makes it very expensive. And it's the same issue when it comes to transportation. Ideally, the most efficient way of, once you produce hydrogen, is to utilize it in the nearest point to keep the cost minimum. Because every time you do the conversion, not only that you will be losing it, first of all, to convert it from one state to another, you will be losing efficiency because you have to put energy into doing that. And then, of course, the associated cost of transportation or to maintain it at such stage is going to be expensive.
Yeah, maybe Professor Yari will give us a solution or something based on that. So we are trying to search a solution for hydrogen engineering in terms of transportation and the storage. And we have our next speaker, Mr. Wolfgang Brand. They will give us, as a matter of fact, more details about this. Dr. Mazen, if we can just one quick question as well. He's asking about giving the likely low efficiency and the high energy consumption of the electrolysis process for hydrogen production. Is it approved as a reliable green energy source by the year of 2030? So yeah, he's also claiming about the low efficiency and high energy consumption of the electrolysis process, and is it visible by the year 2030 or yeah?
Well, actually, is it feasible or not? It depends on so many factors. Now, I would say in a nutshell, if you look at price sensitivity for green hydrogen production, very quickly, if you have a low levelized cost of renewable energy, if you are in a location with high capacity factors, and when you optimize on the capex requirement for the electrolyzers, this will help significantly to reduce the cost of generating green hydrogen. If we select like favorable locations where we have good solar radiation, good wind energy, good combined capacity factor, as of now, because we expect in a decade or so that the cost of electrolyzers will drop, there will be a significant reduction in the cost of green hydrogen production. But as of now, some locations in Saudi are very competitive, and around the world also. If you look at a country like Chile, for example, it's very competitive. So these are the key factors, and it is indeed expected to become competitive as of now, but even more competitive in a decade or so.
Yeah, so thank you very much, Dr. Mazin. So we enjoyed your talk and your answering the question. So as a matter of fact, we had our plan to start with Mr. Wolfgang Brand to give us the matter of fact talk about the global status of hydrogen production and the transportation. So now our next speaker will be Mr. Wolfgang Brand. He is Air Product Vice President of Green Hydrogen. Mr. Brand, as a matter of fact, he joined the Air Product by 2020, bringing about 20 years or more in industrial gases and the petrochemical industry experience. He was the managing director of EMT in Bensberg, Germany, and prior to this, Mr. Brand has various positions of increasing responsibility at Linde AG Engineering, including process engineer, project director, and vice president for petrochemicals business development and sales, and so many other positions. So, Mr. Brand, please, the floor is yours. I would appreciate if you can just limit your talk for 20-25 minutes, and it will be followed by 5 minutes for question and answer. So the floor is yours. Please go ahead.
Thank you very much for this kind introduction. I'm very happy to be here after I had initial security problems with IT, because IT was locking me out of that wonderful conversation that we have now. Glad that it's fixed now. And I think it is now an opportunity to speak after you, Mazen, because this really definitely frames what I'm having to tell on basically your principal presentation, which is like standing on the shoulders of giants. So you already explained very nicely how all that economy around hydrogen will work and the principles. And I now try to give a little bit the frame around what it means in the global context. And I was already eager to answer some of the questions, because like the question for is the hydrogen green in terms of a customer view from a European point of view, that's definitely questions I can answer. Like I was introduced, I'm the vice president for the NEOM Green Hydrogen project. So I'm responsible for delivering the facilities in Saudi Arabia for Air Products. Air Products is one of the largest chemical and industrial gas companies in the world. And we are definitely the one that want to be the first mover in big hydrogen. And so it's my pleasure to speak for the King Fahd University of Petroleum and Minerals. And without further ado, let's go into the topic. Like Mazen explained, the energy transition is fully ongoing. The world has decided inevitably to stop burning fossil fuels. Will it happen tomorrow? No, for sure not. Will it happen in 10 years? Very different in different geographies. So there will be some geographies where you will see the move out of the fossil fuels very soon, and there's other geographies where you will see it in 30 years, maybe in 50 years. But it will happen over time. And that means that all the energy will come from renewable energy sources, mainly solar, wind, and hydro. In some geographies, nuclear is a big thing, and also biological power from converting biomasses. All of that energy will be electricity, and electricity can be, of course, directly used when you have the appropriate infrastructure and energy storage systems, which is mainly the use for light transport, for the municipal use in housing, for heating and air conditioning, for lighting, for light industries. But it becomes a challenge when it is a transport or storage problem, or when it's heavy energy use, because at that point in time, direct electrification is not a good solution, but hydrogen as an energy carrier is. And that market will become a very big market. There was a recent study from McKinsey. I'm not the person that gives you market data because I'm working for one of the companies, not for the market generalists, but they are speaking about a market that is developing 7 to 10 folds from where we are today in hydrogen, for using hydrogen for transportation and in heavy industries. So we think it's a transition, and a transition, like I said before, is not happening overnight, but a transition always needs first movers, needs countries like Saudi Arabia, needs initiatives like NEOM, and needs companies like Air Products to make it happen. Some people just want to have it happen. Some people wish to have it happen, and some states, some regions, some companies make it happen. And I'm very proud to cooperate with Saudi Arabia and with NEOM to make it happen on scale the first time in NEOM. We had already a little bit about that color play on hydrogen. I did very much like when Martin said that you can be color agnostic when it comes to the physical properties of hydrogen. The result is always the same. It's H2, it's hydrogen. And hydrogen is a wonderful molecule for the use as an energy carrier. But the production methodology will help to understand, in principle, on the market value of a product in terms of its further use. Because in some use cases, in some geographies, the way to get there is just limited by the cost effectiveness, and then gray hydrogen from gasification or the transitional steam methane reforming is a very good option and will be a very good option for quite some time. Blue hydrogen, we talk about hydrogen that was produced with CO2 capture, and we can even achieve a negative carbon footprint with that, and I have an example for that a little bit later in the presentation. And green hydrogen, we always speak about when the energy used for the hydrogen molecules are completely green, solar, wind, hydro. And that is exactly what we're doing in NEOM. Let's start with gray hydrogen. Gray hydrogen is 90 million metric tons per year market size at the moment, produced either by the companies like Aramco, like ExxonMobil, like chemical companies for direct use themselves, or being supplied by industrial gas companies like Air Products, Linde, and so on. And at this moment, Air Product in numbers on the external hydrogen sales is #1. And here you see some of the locations. Most locations of the 110 hydrogen production facilities as of today are gray hydrogen. Of course, that's what we did for many decades. Since the last 60 years, companies like Air Products have produced gray hydrogen. But of course, it's a transition. So the next stage in this transformation process is blue hydrogen. And the interesting thing is that the things are very much accelerated, and green and blue is happening at the same time. So we think that blue hydrogen will be ready by 2025, 2026, and the same is with green hydrogen, with NEOM being a first mover. So this is happening in parallel. Blue hydrogen, we're always talking about the same principal conversion mechanisms like steam reforming or partial oxidation, POX, but capturing the CO2. So basically not emitting the CO2, which is one of the major contributors to climate change. And I can give you an industrial example. We just have recently announced the Alberta World Scale Net Zero Hydrogen Energy Complex. So this is a project that will produce blue hydrogen based on the steam reforming and capturing more than 95% of the carbon capture. Now you would say it's not net zero because we are still having some emissions. But on the other side, we are also producing power directly from our production process. And that power basically nets the CO2 emissions to a negative impact actually at the end as a footprint. So the hydrogen that we produce and sell then over pipeline is net zero when it comes to carbon footprint. The ownership is 100% with us. It's an investment of more than $1 billion Canadian dollars in Alberta, Canada, and it will be on stream by 2024. Here I can walk you through the flow chart of such a plant. So it starts reading from the left to right as you do it in Canada. not so much in Saudi Arabia, where we do it the other way around. Alberta natural gas comes in on the left side and goes into the steam reforming process together with oxygen from the air separation unit. And then from the reforming process, we get CO2, which we capture and eliminate by that capturing process, and we produce hydrogen. The hydrogen will be split into use as power to drive our plant to generate the oxygen and to export power to become net zero. And then the hydrogen will be basically sold either, as Martin also nicely explained before, by liquefying for the midterm transport purpose, or we can also inject it into a pipeline, and with the pipeline, we can then sell it also in a combination with other hydrogen. And at the end of the day, at the customer, it's a certification issue if it's a blue or gray hydrogen molecule, and if he's willing to pay for that color difference. Another example is in Louisiana. We also announced a similar facility, and there you have already the combination with ammonia. So technically, the ammonia process is a simple combination of hydrogen molecules with nitrogen molecules as a further energy carrier for transportation. Ammonia is a chemical that is well known and well explored to be used as an energy carrier, can be easily transported, much better in an energy density view than hydrogen. And that's why we use it for both pipeline, but even more for the shipping, as you will see with NEOM. So we announced this facility in Louisiana, where we basically produce a very large amount of hydrogen based on CO2 capture, so it's blue hydrogen. And we also produce ammonia for the export to global markets with shipping and sell it in the pipeline in the United States. So to the pipeline here, a picture. Actually, the pipeline, very much as Martin said, we are color agnostic. The molecules in the pipeline will be all kinds of, we injected from our blue plants where we have carbon capture. We can inject it from conventional hydrogen plants, and we can inject it also from green plants. And by mass balancing, you get the customer, the molecules equivalent to the production method that he's willing to pay for. So it's a very fair process, and we'll make sure that we can serve all our customers with their different needs on blue, gray, and green hydrogen. For Saudi Arabia, of course, in particular, green hydrogen comes into play because, as we heard before, there's a very, very good place in Saudi Arabia with NEOM to produce green hydrogen. And why is this? Because there was also the question in the Q&A. NEOM has a very unique position. It's not only logistical very well positioned, and also very well positioned at an industry project at scale. It also has a very good capacity factor, and renewable power people speak from capacity factor with solar and wind, in that combination of how much wind do you get when the sun is not shining. Because then you combine basically one piece of solar energy and one piece of wind energy. And when the sun is not shining, the wind needs to be there. NEOM has this unique location where you get the thermal wind blowing in at the evening, coming in at the evening and blowing through the night with a very good probability. So basically with the wind and solar together, we get a very stable power supply, a remarkable stable power supply for renewable energy. And we have announced this project and we have started to build it. So there's already activities happening in NEOM. The site is being prepared. The piling contract is now awarded to build these power plants and the process facilities, which will take more than 4 gigawatt of power, of course, distributed in wind and solar, into 2.2 gigawatt electrolyzer capacity, together with a large air separation unit to provide the nitrogen into ammonia, with an expected ammonia production of 1.2 million metric tons per year ammonia. This ammonia is an equivalent value of 650,000 tons, 650,000 kilogram per day hydrogen, which is an equivalent to 25,000 buses in operation. The ammonia will be picked up by ships operated by Air Products, and will be then shipped to places in Europe, United States, and Asia, very much the map that Mazen showed before. And these places we will unload the ammonia and then dissociate ammonia back into hydrogen, releasing nitrogen back to the air. This is a unique process that we have developed in Air Products. And we will introduce these units in the port locations, around 8 locations around the globe. And based on that, we will then supply hydrogen with the main target for the mobility market on heavy vehicles, buses, and trucks. Like shown before, the custom markets for the NEOM project are US, Europe, and Asia. We are dissociating back the ammonia at that places. And then, like said before, the hydrogen will be then either liquefied for a little bit longer transportation or shipped out by pipeline or by direct compression. Hydrogen for mobility is our target market. We know that there's other applications as well, and we serve other applications as well. But we think to make the most impact to the world, one of the things that happen on the first mover side will be the change of the heavy duty vehicles. We have high interest of some cities around the world. We have high interest of logistic companies like Amazon, FedEx, UPS, and so on, to convert their fleet into hydrogen operated fleets and do their part on the energy transition for the world. This will provide safer and more reliable and more cost-effective solutions at the end of the day to the world. We also walk the way we talk. Air Products has started to convert their own fleet, and as an industrial gas supplier, we are operating more than 2,000 trucks around the globe ourselves. And with our partner on the fuel cells, we are converting these trucks and will have our first units operational this year. And we will convert the whole fleet by 2030. All in all, Saudi Arabia has big plans, is very visionary, and is a very important partner to Air Products. Air Products is a leader in global hydrogen, and we have the expertise and investment for the full supply chain to be a first mover at large scale carbon-free hydrogen. And this is exactly what we do at NEOM together. And we are partnering with customers and countries and supply chain on the sustainability journey. We want to be the provider of choice for gray, blue, and green hydrogen to address the energy and environmental challenges, moving us all forward to a cleaner energy future. Thank you, and I'm open for your questions.
So thank you very much, Mr. Brand, for this very interesting presentation. So I think we are ahead of time, so we may have more than a couple of questions. So here we have a question here from Mr. Said. He said, in your opinion, what is your expectation in reforming with CO2 process instead of SMR process? So do you think it might compete with other routes to make hydrogen? So this is his question.
What was the question between steam reforming and?
CO2, reforming using CO2.
With carbon capture.
Right.
I mean, technically, I'm a process engineer by education. So technically, the process is exactly the same. So in the process, you don't change anything. You just have an efficient capturing mechanism to make it more climate friendly and make sure that you don't emit CO2, right? So in principle, you don't change a lot. Of course, there's some tweaks or things that you do differently, but the main difference is the CO2 emission. And inevitably, the customers around the world will no longer be able to support, just from a legislation point of view, from a policy point of view, to use fuel, also hydrogen, that has emitted large amounts of CO2 during the production phase. So over long, the blue hydrogen will completely substitute the gray hydrogen in some of the regions. But again, it's a transition process, so it will happen over time. The next 20 years, we will see definitely both in parallel.
Yeah. So we have another question here as well. He said, what are the side or what are the other products that we can take advantage from the process of hydrogen production? So do we have any other kind of products? This is his question. So we have, as a matter of fact, this meeting has been shared among, as a matter of fact, worldwide, and we have a lot of participants, and they are not, as a matter of fact, of engineering background, maybe, so they may ask such kind of question.
Yeah, which is fine. And honestly, we are considering this on NEOM project. So NEOM, for example, is producing a large amount of oxygen out of the electrolysis process, because you're producing hydrogen. What is left if you put water into an electrolyzer is oxygen. But this oxygen comes at a very low pressure. So it's not very useful for industrial processes or for shipping it out, because you would have to compress it. But we are looking together with NEOM if that oxygen could be a useful thing in their supply chain, in their environment, economics, the environment they are building up. Fish farms was one of the things that was mentioned. Maybe that oxygen could be a valuable byproduct. So that's definitely something that you could consider, because technically what you do is you put water in and electrical power in, and you produce hydrogen and oxygen. The ammonia process itself doesn't really produce any byproduct. So compared to petrochemical or oil and gas, we are very lean in what we produce, because we don't handle a lot of different molecules in the hydrogen business, right?
Yeah. Here is another question, but I think most probably maybe
one thing, waste heat is also something that could be considered, because the electrolyzer are generating a lot of heat, because technically what happens is if the power goes in, it either produces hydrogen or it will end up in a form of heat. And though the waste heat could be also an interesting byproduct for other industries or municipal use. So waste heat and oxygen are basically the byproducts. Sorry.
Yeah. So here is another question, as a matter of fact, is talking about something related to the acceptance of hydrogen as a fuel in the new economy for hydrogen economy, the societal acceptance here. I think this question maybe Dr. Mohammed Ahmed, inshallah, will be responding to it maybe, or if you have a comment, he say, how do you plan to drive the demand to change the customer behavior so that as we are targeting the mobility sector? So he's asking how people can accept such a kind, maybe he's thinking about the risk of dealing with hydrogen. So how safe, we can say, we can translate this question, how safe is the use of hydrogen in mobility, like fuel cell electric vehicle?
Yeah. Let's put that question in two questions. One question is about the policy side, the regulation side, and one question is about the customer expectations. On the policy side, we are very closely looking to what Europe is doing, because Europe is very good in bureaucratic things, like setting up the right standards, like this, what they call the Renewable Energy Directive. And we are making sure that the NEOM product complies with that specification and regulation. So basically, if a certain policymaker says, only under these conditions, we call it a renewable fuel, then we will be ready to certify that. So that's the one side. The other side is the customer expectation, in particular when it comes to safety and the change process. Safety is relatively easy to answer, because we make it safe. Well, hydrogen is safe because we make it safe. That is how you handle hydrogen. Generally, a diesel-operated car is definitely not less or more safe than a hydrogen-operated car, because hydrogen, if you handle it correctly, goes to the air, right? You don't get pool fires and all that nasty thing that you have with diesel cars. It's more a process about convincing people that this is not the Hindenburg case. The hydrogen car will not just simply explode. And that will take some time and quite some effort to convince the customers. But our strategy is to work with the fleet operators for buses and trucks, because that is definitely something that the customers will more easily understand and accept. It's not individuals entering into a bus just because the bus is hydrogen operated, because you trust the bus operator, right, that everything is safe. So you will not avoid buses that are hydrogen buses. But we need to convince the operators, of course, that it is safe, together with the fuel cell operators.
Yeah, so last question that I really like, it's related to the internal combustion engine. So he said, as a matter of fact, is there interest to use hydrogen internal combustion engine for mobility? I have been working for years in internal combustion engine, and I don't like, as a matter of fact, to let it go. So, so what is the possibility for this comparing to fuel cell and other issues?
You know that I'm living in the city of Munich, and the city of Munich is the BMW city, and BMW is having cars with hydrogen direct combustion. They have not developed them in a cost-effective solution for the masses at this moment, but if the customers are interested in, then it will happen. I think the large amount of the market will go to the fuel cell because that is what seems to be more cost-effective. But the hydrogen combustion could be an interesting alternative, in particular for high-performance engines. Definitely, it is a technology that is proven and it's workable. Will it be a technology that is widely used? I'm not so sure of that, but will it be a technology that exists and have its use case? Yes, maybe Formula One cars will operate with hydrogen in the future.
Yeah. So thank you, Mr. Brand. We really appreciate your presence here with us. And thanks for this presentation and being patient to answer those questions. As a matter of fact, we have a lot of questions, so you can look at if you have some time, you can kindly answer them. So next speaker, I'll be moving to the next speaker. We have a very special speaker tonight. We have Professor Omar Yaghi. As a matter of fact, like our other speaker, we don't need to present. Professor Omar Yaghi is a professor at University of California, Berkeley. He has been shortlisted for the Nobel Prize, and for sure, inshallah, very soon he will be holding the Nobel Prize. And we are delighted, as a matter of fact, to have him tonight to give us a talk on the recent development in hydrogen storage materials. Professor Omar Yaghi, he got his bachelor degree from the State University of New York, Albany in 1985, and the PhD from University of Illinois, Urbana in 1990. Postdoc in Harvard University for 2 years, and he has been in the faculties of Arizona State University, University of Michigan, University of California, Los Angeles, and is currently, as a matter of fact, the chair professor of chemistry at UC Berkeley, and a lot of, as a matter of fact, elongated list of prizes and positions. So we don't have time to talk about. We really want to hear to Professor Yaghi. So, Professor, the floor is yours. Please go ahead. So I will be just sharing.
Thank you very much. Yes, thank you for doing that. Yeah. Let's see.
So do you see it, Omar?
Yes, very nice. Thank you. Thank you very much, Madhat, for that wonderful introduction. And it's a true pleasure to be here and to be in Saudi and to be giving this online talk. I'm sorry I can't share with you my video because I happen to be in a car. But anyway, you won't know while I'm talking. So I want to share with you our work on hydrogen storage in MOFs and some of the results that we have obtained over the years. Next slide, please. Before I do that, I'd like to just show this slide, which I extracted from the literature, about the different ways of storing hydrogen. And there are physical means, of course, where you either cool the hydrogen or pressurize it or do both. And these are energetically costly, and they require very expensive equipment and special kind of containers. And then there's on the other side, material-based approaches. And these vary from adsorption, where the hydrogen is interacting weakly with the material, but also there are other materials that require you to bind the hydrogen, split the hydrogen, bind it as an H with a hydrogen strong covalent bond to the substance, to the material. And I would say, I don't want to dismiss all of these different techniques because they don't involve MOF, But when you have hydrogen bound through a covalent bond to a material, it first of all costs energy to take it out and to evolve the hydrogen, but also the materials, such as in the case of alloys and the chemical hydrides, the material eventually decomposes and it loses its reversibility. In the case of alloys, they become brittle and they lose their effectiveness. This is why I have been working on the idea of adsorption in porous materials. So, and that's the topic that I want to discuss today. Next slide, please. So just so that we are all on the same page, for an automobile, just an average, let's say, size sedan, you need, for petroleum, you need around 24 kilograms of petroleum. For hydrogen, you only need 4 kilograms of hydrogen to travel the same distance. This tells you that the hydrogen is energetically more rich than water, than petroleum. So this is really what we want to be aiming for, is the storage of about 4 kilograms of hydrogen at room temperature, if we're really interested in using hydrogen for automobile fueling. Next slide, please. Yeah, 4 kilograms of hydrogen translate into a balloon or a container that is 45 cubic meters in volume or 5 meters in diameter. And of course, none of us, especially in large cities like Riyadh, want to drive with a fuel tank like that. So without increasing the size of the current fuel tank, can we find materials that can compress hydrogen within them through this adsorption process and get enough hydrogen to use it for automobile fueling? The answer is not yet, but we have made progress. And the progress comes in terms of the design of the material. No, you got it right. Next slide, please. Progress comes in the following way. You take a material, and if you want to store enough hydrogen in it, you want to expose every single atom in that material and make it a surface. So that now every atom becomes one could say, a parking spot for a hydrogen molecule. And if you have a very high surface area material, like what I'm showing here on the right, you're going from a particle that only has, let's say, 1 cubic meter per gram, depending on the size, but small particle. And then you can turn that particle, if you turn it into a porous material on the atomic scale, you'll get to 7,000 meters square per gram. That's the kind of surface area that you need. And it comes from the fact that you're exposing almost every atom in the structure for adsorption of gases. We have worked on hydrogen, but also carbon dioxide, methane, and water. And that and such a material is called metal organic frameworks. They're made from metal oxide corners, you see here in blue, and organic that links them together. And all these spots that you see as spheres are atoms that are, we know from X-ray crystallography, not just the structure of the MOF, but also we have observed both hydrogen and other gases bind to each one of these atoms that you see here. So everything you're looking at in a MOF is actually an adsorptive site. That's why they have extremely high surface area. Next slide, please. Yeah, next, okay, yeah. So you see here hydrogen gray and the MOF in red. And the idea here is that you build a material that attracts hydrogen to it, but without making a covalent bond between the hydrogen and the material. And so you want to pack the hydrogen as much as possible on the internal surface, of the material. And you see here in this model, you see a lot of open space in the middle. So that means that this material has a pore size that is just too open, too large for hydrogen. It needs to be able to fit 3 hydrogen molecules sitting next to each other. That would be the optimal size, which is around 7 angstroms in diameter for the pore size. So that's the ideal pore size. In this particular case, this is not quite ideal because you're wasting a lot of volume there that wouldn't be occupied with hydrogen. So next slide, please. So the requirement then is that we have, with MOFs, we have well-defined materials, we have high surface areas. That means more adsorptive size for hydrogen. We have, because the structures are very open, hydrogen can go in and out with great ease. And we need a pore size of around 7 to 8 angstroms. That's not very difficult to do with MOFs. For some of you who are familiar with the chemistry, you can vary the length of the linker and you can achieve 7 to 8 angstroms. And of course, with MOFs, we are able to vary the composition of the metal oxide units, as well as in terms of changing the metals, different metals, and we can also vary the functionality on the organic units. So we can fine tune the pore size and the chemistry of the pores to, let's say, in the hope of enhancing the adsorption of hydrogen. Now, one parameter that everybody who works on hydrogen storage in porous materials by adsorption mechanism, by physisorptive mechanism, is the adsorption energy. The adsorption energy need to be around 20 to 25 kilojoules per mole. That is basically the strength of the interaction of hydrogen to the material, and it's the maximum strength that you can obtain without the hydrogen making a covalent bond to the structure. So anything above that is going to cost you a lot of energy to take out, and because you will be forming real covalent bonds. So that's the objective. And here's a MOF 177. This MOF takes up 12% of its weight in hydrogen. That's a lot of hydrogen. Okay, and you can see here the isotherm. It's been verified in different facilities around the US. But this uptake is at 77 Kelvin. Okay, that's higher than 20 Kelvin, where hydrogen is a liquid. And it's the temperature that a lot of hydrogen is being transported across highways in I know in the US and probably in other places. So what does 12 weight percent mean? It means that if I have a tanker filled with MOF, I can transport double the amount, keeping everything else the same, temperature, pressure, everything the same. And so this is very interesting for transportation of hydrogen in these big trucks, and also for stationary applications of hydrogen storage. But at 77 Kelvin, at this level of uptake, you're not able to get too much at room temperature, and therefore this is not as interesting for automobile fueling. For automobile fueling, we need to be able to get at least 6% by weight, and at room temperature, not at 77 Kelvin. So this is a good start, and we have learned basically what it requires, what kind of structures would be required to develop materials, not just materials that are good at storing hydrogen at 77 Kelvin, but also at room temperature. Next slide, please. So clearly, the surface area matters. You can see here the amount of hydrogen that you absorb in milligrams per gram plotted against the surface area, and you see there is a direct correlation. The higher the surface area, the more hydrogen molecules you're going to have on those absorbed on the internal surface of the material, the more hydrogen you store. But you have to be careful, because as the structure becomes more and more porous, if the pore size gets larger and larger, which doesn't have to be, you can get very high surface areas with small pore size, meaning a lot of adsorptive size, but yet your pore size is appropriate for hydrogen. But you could also get very high surface areas with very large pores. So you want to make sure that you get the high surface area with the 7 angstrom to 8 angstrom pores, so that you're not wasting volume in your fuel tank, as I showed you those openings in the MOF in the video. So you want to obtain good, not just good mass percent, but also you need to get good volumetric uptake. Next slide, please. So one of the tricks that we've been using beyond just using a MOF, as I showed you, we have been exposing the metal sites to create more stickiness to the hydrogen or higher binding energy. So here's a MOF where the copper sites shown here in yellow originally have water on them. You can heat this material up and expose the copper sites, and then that gets you a stronger binding energy. Next slide. This is just another illustration showing the copper in yellow, but you can see it's replete with open metal site onto which hydrogen can bind. And that's fine. Next slide, please. And it works. I mean, when you expose the metal sites, you get the best hydrogen storage material. You get improvement by about 75% from the material without the metals exposed. And the room temperature storage for this material is 2.5 weight%. Okay, so that's at room temperature. That's not bad. 2.5 weight% is a lot of hydrogen. Okay, that's by weight. It's a lot of hydrogen, but it's not yet at the 6% level that we need to get the automobile industry excited about using hydrogen in the BMWs and Mercedeses of the world. Next slide. Even at this scale of about 2.5%, Mercedes found it exciting enough to put it in one of their demonstration models. This has a tank that is filled with MOF, pressurized with hydrogen. It is at room temperature, but again, this one is pressurized at 600 bar, which is not the DOE requirement. We need to be able to get enough hydrogen at reasonable pressures that are not going to cause danger or use heavy tanks. So around 100 bar or so is the objective. Next slide, please. So if indeed that hydrogen fuel tank was on the road, your fueling time would be 2.5 minutes. This is the fueling, uptake and release repeatedly. And because you're not making chemical bonds between the hydrogen and the MOF, and just physisorptive forces or polarization forces, the hydrogen can go in and out with great facility and without leaving an imprint on the material like those chemical hydrides or the alloys that I have discussed before. So you don't even need to heat up the material. Just by releasing the pressure, the hydrogen comes out. Next slide. Okay, so this is just a comparison. It just says that for room temperature storage, for adsorption materials like MOF, we're doing well. We have made progress by modifying the MOF. Our adsorption energy, remember I said we need 20 to 25 kilojoules. So far with that open metal sites, we have about 13 kilojoules per mole, which is an improvement over the one that doesn't have open metal sites, which has around 3.5 kilojoules per mole. So we're making progress. And I think that shows the power of this chemistry. We know, next slide, please. We know where the hydrogen is going, and it's exactly where all other gases go, on the phenylene units, on the edges of the phenylene units, as well as the metal oxide units. So, but we need to create a more stronger adsorptive sites than these metals, or change the metals so that we have a way to modulate the adsorption energy. Next slide. I just want to say that if you pick your metal right, metals that have lower oxidation states, you can have this situation, bonding of hydrogen to the metallic unit. Hydrogen is both a Lewis acid and a Lewis base. And so it is able to donate electron density into the metal, as well as the metal can donate a density back into the hydrogen. And when the metal donates back into the hydrogen, it weakens the hydrogen-hydrogen bond. And basically you have a situation of what I call soft chemisorption. You have some kind of bonding taking place between the hydrogen and the metal, but it's not a full-fledged chemical bond that you need to heat up the material to very high temperature to remove the hydrogen. This is, if you're interested in hydrogen storage at room temperature, this is what you need to aim for. This is what we are trying to aim for. Low oxidation metals in a MOF that then can attract hydrogen at a level that we want. There are some theoretical calculations also that show that if you take lithium and you impregnate lithium into hydrocarbon linked MOFs, you could get very easily to 6% at room temperature. Okay, next slide. That's just another set of hydrocarbons. It's the same idea. Lithium goes to the hydrocarbon center, it makes lithium plus, and then potentially it could bind hydrogen. It's not as easy as it looks in the lab because lithium loves to hang onto solvents. So you have to desolvate, and hopefully you can still get the lithium to not aggregate into nanoparticles. So next slide. So more work to be done there, but it's possible. It's also possible if you what I call super metallate them off. It creates just the high density of open metal sites of the right metal. That's another approach. Next slide. Okay, so in the end, what I want to say is that we are, in terms of room temperature storage, we are at a binding energy of 13. We need to almost double that to 20, 25 kilojoules per mole. We need to use metals for soft chemisorption. Physisorption alone is not going to get us there. And we already have high surface area materials, so we need to maintain that, can't compromise that. We have stability, we have kinetics, we have regeneration. All of those are working in our favor. So all of us who are working on hydrogen storage, the holy grail is number 1 and number 2. So we have still more work to do, but it's an exciting scientific problem. And the nice thing is that we have been making progress, and MOFs are extremely tunable and very flexible in terms of changing their modules and trying to get to the right material. Next slide. Yeah, okay, thank you. I'm happy to answer any questions.
So thank you, Professor, for the very interesting presentation. As a matter of fact, hydrogen, the main problem in hydrogen is not the production. Already we have well-established technology for hydrogen production, but still the problem is hydrogen engineering in terms of mainly hydrogen storage and transportation. So I will stop sharing so that I can see some, I can see the questions. So we have a question here, Professor. He is asking, any comment? He is asking about the MOF degradation with number of fills. So is it degradable with time, or how many times we?
Well, yeah, MOFs. MOFs, as you know, if you've been reading the literature in the last 5-6 years, MOFs that are stable in acid, base, thermally stable, long-term stability, have been made and reported and scaled up to multi-ton quantities. If you heard me talk about water harvesting, MOF 303 is a MOF that is extremely stable, long-term stability in water. So the stability is not an issue for MOFs, especially when you have physisorption. No chemical bonds are being broken with the hydrogen going in and out. So I don't see this as a problem. And then not to mention, of course, COFs. Now, in the last 2 years, we have been successful in making COFs that have a carbon-carbon bonded backbone. Those are extremely stable. Those are porous crystals that are extremely stable in very strong acids and bases, refluxing acids, bases, water, all solvents. So the ideal materials in terms of stability exist. It's a question of functionalizing them and getting that binding energy to be higher than what we have now.
Yeah, So another question I think Yani, is very similar. He said, does retake of hydrogen from MOFs require desorption of this MOFs? I think desorption of hydrogen. And will it be durable for several times of uses? So I think already, Professor.
Yeah, I think they're very, very cyclable. You're not breaking any bonds. Even the water, when water goes into the pore or CO2, we can cycle for thousands of cycles. With water, tens of thousands of cycles. So yeah, those questions about stability, cyclability are not an issue for MOFs, not at all.
Yeah. So, Professor, we have here a question from Dr. Hassan Al-Fahtani from Saudi Aramco Advanced Research Center. He is asking, have you done any research using this material on hydrogen or even carbon dioxide storage under subsurface condition? Maybe high under elevated temperature and high pressure condition?
High pressure is okay. High temperature, you have to limit it up to 300 degrees Celsius. Okay, but no, we are not under the surface. We have not done any studies there. We have done geologic pressures on MOFs. And it was a way for us to figure out the point of breakage of the architecture under geologic pressures. And some of them we published actually one paper a few years ago. Some of them are remarkably stable because they have, I would say, zero stress points. If you look at those metal oxide units, they have opposing 90-degree interactions as well as twisted 90-degree interactions when they're opposed to each other. And that's a very nice way of absorbing energy or stress energy. So they turn out to be extremely stable under a very high pressure. So no, I would love to collaborate with someone at Aramco to stick MOFs under there and see what happens.
Yeah, thanks, Professor. So I think Professor Omar now is available at KFUBM. He's leading the consortium for sustainable future. And I think, inshallah, we should have the chance to work, inshallah, together. So we have another question. He said, is MOF available commercially and how to characterize them? So how to characterize them? So something, and I think the question, MOF, is it available commercially or is there a way for?
Yes, you can buy. You can buy them from Aldridge. They're available. You can, if you want kilogram or ton quantities, you can buy some from BASF. But there's also a lot of what should I say? Startups, I guess, that are focusing on that. But it just depends on the MOF. I think that there are about 24 MOFs out there, but if you have a specialized MOF, you would have to collaborate with someone on scale up.
Yeah. So
and of course, they're characterized by typical characterization techniques for solids like X-ray diffraction, NMR, other spectroscopies.
Yeah. So thanks, Professor. So yeah, as a matter of fact, yeah, and we have a room of maybe 4 minutes or something. So just we need to take this a chance to hear from you. So we have the question from Dr. Abdullah Al-Abdali, I think, from KAXT. As I guess the name appeared to me, we have met together here at KFUBM, and they are working also. They have interest in CO2 capture. He have a question. He said, how would the impurities such as carbon monoxide or dioxide affect the permeance of MOFs?
Affect what? I'm sorry, I didn't hear the last.
Maybe, I think maybe the question is not maybe well written, but he may ask about impurities. What is the effect of impurities in, let's say,
impurities.
Yeah.
Impurities, well, it just depends on the MOF. I mean, if you're talking about the coughs that I just mentioned, they would be extremely stable if you have, corrosive impurities like H2S or amines. If you have, it just depends on the MOF. Depends on the MOF, depends on the cough. You can't generalize. You just have to match your application to a structure, okay?
So we have here somebody is asking about, he said, what are the challenges with heat? Maybe he means atmospheric temperature, which is very high. He said it's about 50 degrees here in Saudi Arabia. So I didn't really get this question point of view, but he said the challenges with heat in relation to the operation. So I think you have already.
I don't see any problem with the heat. No, I mean 50 degrees is nothing to break carbon-carbon bonds. You need a lot higher temperatures.
Yeah. So another question here, Professor, maybe is the last one. He said, how do you compare MOF to conventional zeolites?
Well, I mean, zeolites have their own applications. MOFs offer you, of course, all the design abilities, and especially for hydrogen, you have a high surface area that you can get with zeolites. You have the ability to fine-tune the structure that zeolites don't have. I mean, we wouldn't have gotten to 13 kilojoules per mole had we been working with zeolites. So, because I think tunability is very important. Zeolites are very important materials, but they're not, I wouldn't say they're the 21st century materials, because the 21st century requires materials that are, that could be crafted on the atomic molecular level.
Yeah, great.
For
So,
many different applications.
yeah, so thank you, Professor, very much for being with us tonight. We are highly delighted with this meeting. And you can see we have many questions, as a matter of fact, are coming on, and a lot of appreciations to be with us tonight. So thank you very much, Professor Omar. And
Thank you.
I know you have other commitments, so please.
Thank you so much. Thank you.
Thank you. Yeah.
Bye-bye.
Bye-bye. So we still have another presentation here. We have at last we have Dr. Mohammed Akimaya at last, but not at least for sure. We have Dr. Mohammed Akimaya is assistant professor here at KFUBM. Dr. Akimaya has received his PhD in mineral and energy economics from Colorado School of Mines. He got his master's degree from mineral and energy economics from the same university. His bachelor degree in electrical engineering, so not only economics, he has electrical engineering background. So he has a clear background about the engineering problem of hydrogen. He got his bachelor degree from Bordeaux University. He have also experience. He previously worked for PB Megas as an Indonesian state upstream oil and gas activities regulator as an assistant to the deputy chairman for financial control. Dr. Mohammed Akimaya will be speaking to us tonight about the challenges in setting socio-economic models for the hydrogen economy. And as a matter of fact, we have received a list of questions talking about this issue of economical acceptance and policy and all of these issues related to the hydrogen economy. So Dr. Mohammed, the floor is yours, please go ahead.
All right, thank you very much, Dr. Medhat, and thank you for the Center of Hydrogen Research in giving me this opportunity to talk a little bit about the hydrogen economy. So first of all, let me share my screen. Okay, so what I'm going to present is basically, kind of an economics take when it comes to hydrogen economy. So from the previous speakers, they're focusing, pretty much more towards the, engineering side, the science side of it. But since my background is more towards an economist, I'll talk more from the perspective of economics, and hopefully it will, provide some sort of a different perspective when it comes to, how economists are actually seeing this hydrogen economy. Is this sustainable? Is there really a future in which hydrogen economy would actually prevail. So first of all, wait 1 second. Okay, right. Sorry, I'm a little bit lost. Okay, all right. So I'll start my presentation. So I will, first of all, I will talk a little bit about background about hydrogen economy from the perspective of an economist. So obviously, hydrogen economy, based on the previous presentations, obviously you probably have a good idea right away when it comes to hydrogen economy. I'll talk a little bit about the current trend in research, or you probably have an idea about the current trend of research based on the previous speakers as well. But I'll add the problem of, it's not a complete picture when it comes to the research, when it comes to how hydrogen economy is being approached from the perspective of what's happening in the industry and also in academics. And then I'll talk about the hydrogen demand issues, hydrogen economy model, and the role of the government, and I'll conclude based on that. So first of all, what is this hydrogen economy? To put it in simple terms, basically hydrogen economy is just, when you have some sort of like an ecosystem in which we rely on hydrogen for our energy. So basically there has to be some sort of utilization, some sort of production, but it creates some sort of an ecosystem. Why would hydrogen be, or this hydrogen economy become so attractive? People are claiming that, okay, this is the right way for energy transition. So the main idea when it comes to hydrogen is that, if we rely on renewable energy, unfortunately, renewable energy has issues regarding their reliability, because when it comes to renewable energy, there's an issue of intermittent. Sometimes you have it, sometimes you don't. So you kind of have to develop some sort of energy storage to support renewable energy. We can't also just focus on or stay with fossil fuels because it harms the environment. There's climate change. And hydrogen is supposed to be, kind of the breakthrough, the solution to this energy transition towards a cleaner future with cleaner energy. I'm gonna paraphrase what has been mentioned by Mr. Wolfgang previously. Okay, so in order to have this to become a reality, obviously there has to be some sort of an analysis. And from the perspective of economics, okay, there's not just about the production side, but in our glasses, we need to have an idea about from the consumption side as well. So there has to be some sort of analysis, some sort of research that's focused on, okay, so if we are going to have this hydrogen economy, what would it look like? What's the market representation of this? And with this kind of market, is this some ecosystem would require specific policies, specific regulations, or we can just leave it as is? Not only that, the third important thing about providing an appropriate analysis when it comes to hydrogen economy is, okay, what would be the future of research and development in order to make sure that this hydrogen economy becomes a reality? So if we look at the current trend of economic research on hydrogen, basically, if you just go to Google Scholar and then just type in hydrogen economics or hydrogen research, most of them are techno-economic analysis. The focus is always going to be about the production cost of hydrogen. What's the levelized cost of hydrogen? With different colors. Oh, this is the black one, this is the gray, blue, green, teal, I don't know. There's a lot of colors. And I think different institutions have different color schemes. And what about if the infrastructure is different? What about if the geographical location is different? What if this hydrogen production facilities is located near a natural gas reservoir? What about if it's near to coal mines? So there's a lot of, how would that affect the production costs? And lastly, about the end product as well. Would it be hydrogen, or should we actually transform it into ammonia? So first of all, it's about hydrogen production costs. Secondly, it's about hydrogen storage costs, which was, pretty much obvious based on the previous, presentation. And also hydrogen transportation costs, okay? How expensive would it be to transport hydrogen? Should we liquefy it and then use shipments for hydrogen, or should we just use pipelines? These are the current trends of the economic research nowadays. This presents an incomplete picture of, from the eye of economists. This is an incomplete picture. What's wrong? So the issue is that when it comes to production side research, it focuses on the supply side only. And the main premise is always going to be, as long as the product is cheap, it will definitely attract customers. Now, from economics perspective, there's a major flaw in this premise, because we are assuming that the price is the only factor. As long as it is cheap, it will definitely attract customers. When the price of the product, if the production cost is low and the price is relatively cheap, there will be some sort of economic feasibility. But actually, it's not always true. Economic feasibility doesn't necessarily mean, cost minimization. I'll give you an example, a very simple example. You can buy 50 of product A. I'm not going to tell you the product. You can buy 50 of product A for 10 real, or you can buy one of product B for 1,000 real. Now this, if I ask you which one should you buy, basically you can't really say, right? Because, oh, wait a minute, what is this product? Is this, a same product in terms of usefulness, in terms of usage, or are we talking about entirely different product? So one is actually a straw, while the other one is actually, a kind of like a used iPad. Now, obviously, once you see the product, you have some sort of idea about, oh, the attractiveness, or, oh, with this product A or this product B, what can I get out of it? And this is what makes a product attractive. So when it comes to hydrogen demand, the issue is, we need to have some sort of a clear picture, a clear idea about the usage and the benefits. And this product might or might not have substitutes. And what are the features of it? These features would dictate what the consumer's preference would be. And depending on consumer's preference, a product can be free but still under-consumed. An example of that would be, in the current days, that would be about vaccine. In some countries, vaccines are free, but still you don't get 100% vaccination rate. It's still, quote unquote, under-consumed. So it's not just about the price, but consumers' preference can actually, build some sort of responses in the market that would create, a condition where, okay, there will be a lot of sellers, there will be a lot of production, but at the end of the day, who's going to buy this? Now, if we look at hydrogen, obviously, if we relate it back to the reason why hydrogen economy was so attractive is that when it comes to hydrogen, it's about the energy transition, phasing out fossil fuel. And the reason for this is to tackle the issue of climate change. It will bring environmental benefits. It will bring less pollutions. So it will free up the air. We'll have cleaner air, so it should be good for everyone. So, but wait a minute, we're not really sure about this hydrogen utilization yet. How can we actually achieve this less pollution? in what way would hydrogen utilization reduces pollution? So somehow, some way, it's a little bit answered from the previous presentations. But when it comes to the current demand for hydrogen, mostly it will be for industrial purposes. In the chemical industries, for ammonia, in refineries, and iron and steels, and cement. If we're looking at utilizations of hydrogen for this industrial purposes, notice that this will not bring a significant impact on the environment. Why? Because, well, you're just using hydrogen for producing other products, other output. So how would that relevant to our climate change issue? So of course you might say, oh, wait a minute, maybe the current hydrogen that is being produced, which is the gray or the black hydrogen without any kind of carbon capture, then obviously, yes, you can have some sort of effect, you can have cleaner hydrogen, but will this bring us towards tackling the issue of climate change? I would say that's arguable, because look, of course, you will reduce the pollution because you won't be you will be capturing carbon based on hydrogen that you produce initially. But what about the other fossil fuel industry, the other sectors that actually use fossil fuels? So that, in order to have a significant environmental impact, the hydrogen have to be used in place of fossil fuel energy source. It has to replace fossil fuels if the main goal of hydrogen is to actually, be the solution to climate change, the solution to energy transitions. So there are two ways of doing this. It's either hydrogen as an energy source, but I think it's kind of answered based on previous presentation by Mr. Wolfgang. But hydrogen, probably not as an energy source, but more towards as an energy carrier. So in that sense, the environmental impact of having hydrogen would be huge if hydrogen is being used, for example, as a fuel for example, cars that use hydrogen-based fuel cells or hydrogen-based fuels. In this sense, then yes, that would have an impact in terms of, okay, the pollution is mostly coming from transportation industry. Now, if we replace the transportation industry from fossil fuel based to hydrogen based, which is relatively no emission, then obviously, yes, we are going to have a big impact on the environmental issue into the climate change issue. But even then, we're not really sure, will it be in the form of hydrogen? Will it be in the form of ammonia? Based on the research that I have seen, well, it's still not clear about, what kind of form when it comes to hydrogen, the product itself, when it comes to, mobility industry or automotive industry, what kind of form would it be once it reached the final consumers, when it reached the people, the population? Because at the end of the day, it's not about, making sure that the price, the cost of production as low as possible. You also need to consider the fact that, look, the product itself has to be attractive. It has to bring some sort of consumers' behavior that wants to actually purchase that. Because if you're looking at the environmental impact alone, and if we're just looking at the environmental issue, at the government level, because of the Paris Agreement, because of the cooperation between different countries in order to achieve this climate change solution, sure, it probably might be sufficient to act based on, okay, we can have some sort of environmental impact if we rely on hydrogen instead of fossil fuels. But what about at the individual level? Because at the end of the day, the final consumers will not be the government. Sure, you can probably say, okay, we'll just have the government, setting up things for us, but that would bring some sort of cost to the government. Is this sustainable? So I can see right away from the individual level, when it comes to environmental issue, there are always going to be questions. The most common ones are the three that I have listed here. Why should I be paying for things that I don't do? For example, okay, the environmental issue is being caused by, for example, coal power plants. So coal power plants generate electricity, emits carbon, harms the environment by, this air pollution. I'm not the one doing that. Why should I be charged? Why should I be, involved in terms of solving this issue? And if I'm poor, why don't I just say, look, there are rich people. Shouldn't they be the one who pays for this? And lastly, if you don't really feel the benefit, why should I do it? Right? For some countries that have issues with air pollutions, then obviously, yes, you probably are aware about the issue of environment. You feel the need to actually act upon the fact that, oh, our air is polluted. We have to do something to change it. But if you don't really see the fact that, oh, our air is polluted, if you go outside, it looks like air is, pretty much clean. I don't think it's problematic. Then why should I do it? Okay, this brings up the issue of externalities because, the problem is probably not from me. The problem is from the outside. Why should I be involved? So when it comes to the benefit of this hydrogen, first of all, we need to know from the economics perspective, we need to know what is the utilization, what is the main target of this hydrogen, what's the product, the actual product of hydrogen that will be delivered to the people. Of course, in terms of benefits, if I'm using this product, obviously, for those people who are aware about climate change, there will be less guilty about, we're not contributing to the environmental pollution. But one thing for sure, in order to be attractive, at least the satisfaction of this product has to be the same as if you're using fossil fuels. So this probably explains why most of research currently is about making sure that, production cost has to be at least the same price as the fossil fuels. But in reality, probably that's not what the consumers or potential consumers are seeing. So in reality, it's a different technology that requires different infrastructure. For example, we take an example of hydrogen fuel cell vehicles. So fuel cell vehicles based on hydrogen. So first of all, if I'm a potential buyer, the very first thing that I would ask, well, is this really useful in the sense that, would there be a problem with it? Well, what about its safety? I think this, was asked before, wouldn't it explode all of a sudden? What about its reliability? If it was mentioned just now, 4 kilograms of hydrogen can get you to 450 kilometers, if I remember correctly. But how reliable that is in terms of, when you're really driving it? What about its lifetime? This car, would it last 5 years, 10 years, or would it last 20 years? And the most important thing is, well, I already have a vehicle, I already have a car. Why should I pay money in order to actually change my car to this new car. So obviously, having the same price in itself probably is not going to be enough when it comes to making sure that the actual product of this hydrogen is attractive. Then also there's also the perspective of social benefit, of course. With the hydrogen economy, it will create an ecosystem. There will be production, utilization. It can create jobs. It can improve standard of living. But as an individual, would I really be affected with it, or would I not? And I'm not talking about if me as an individual, but I'm talking about the aggregate people. If we add up all of the people, what would they feel about it? And this brings up the hydrogen economy model, and this brings up the big challenges when it comes to actually trying to capture or illustrate, represent the model that would be appropriate from the economics perspective. So obviously we'll have production, storage, and transportation. We have the economic benefit, the environmental benefit, and also societal benefit. The production, storage, and transportation, these are the costs that would dictate the price of hydrogen. And on the right, we have the benefits that would dictate the attractiveness of hydrogen. Now, one thing for sure, when it comes to this hydrogen economy model, in order for this hydrogen economy to be sustainable, the benefit has to outweigh the costs. It has to be attractive enough that when it comes to the market of hydrogen, it's attractive. Not to mention that from the cost perspective, from the supplier's perspective, they also need to make profit out of this. That's how we can make a hydrogen economy sustainable. The issue, to sum up what I have been mentioned, the environmental and the societal benefits, it may not be felt and might not be seen by individuals. So when we're talking about, okay, would this hydrogen economy persist? Would it be sustainable? Well, you have to look at the economic benefits. You have to look at the individuals. And currently, you don't really have that. So in order to sum it all up, I'm going to wrap things up a little quicker since I'm close to running out of time. The hydrogen economy issue from the production side, what about the current hydrogen production? Are we going to implement some sort of policy in order to replace gray hydrogen with green or blue? And well, obviously, if we're going to do that, there will be a cost to the industry. And that would bring a ripple effect to all of the products based on those industries. We have to look at the impact of that. Different characteristic of the country. So different country have different characteristics. Some country might be more beneficial to develop green hydrogen, while others about blue hydrogen. And about scaling up production. So I did a research with KCAR. So would other sectors be able to support it? For example, for Saudi Arabia, if the government or Saudi Arabia decides to pursue this green hydrogen, that means it has to have the infrastructure, the water infrastructure, and also the pipeline infrastructure in order to transport the hydrogen, and also the electricity sector. It has to be supported by renewable energy. With scaling up production will be a problem. From the consumer side, this is a bigger issue when it comes to production side. There's a lot of research on it, but when it comes to the consumer side, hydrogen is just an energy carrier. What is the actual product? Until now, I'm still not seeing what's the real main target of hydrogen. I'm assuming it will be about mobility, as what was mentioned just now. And in this scenario, yes, it will have a great impact on the environment. But when it comes to the actual product, before we can do any kind of analysis on consumer preference of this product, we can't really say anything. Because why would an individual want to shift to this, for example, hydrogen-based fuel cells? Of course, the government can play some sort of role. They can implement such a policy. the role that the government can play, obviously, in providing incentives, they can tilt the balance. There's a cost of producing hydrogen, and there's a benefit of the hydrogen product. So the government can kind of tilt the balance, but if it's not sustainable, the government will be, paying the burden of, making sure that the balance stays constant. So from the perspective of, the government perspective, the policy makers, you need an appropriate socio-economic model in order to ensure that you can make an efficient policy formulation, making sure that you're not going to waste a lot of resources, a lot of money for something that's probably inefficient. And you should probably be able to dictate, if turns out that, based on our analysis, this is what's good for our country or what's good for the market. So the direction of future development has to follow that step. Now, to look at the current research on utilization, this is the issue that there's a significant gap in the literature. And most research assumes that the demand exists. So it's just government have some sort of maneuver, some sort of policy. They want to create the demand for hydrogen. But at the end of the day, again, it will be individuals who have to be paying for this. And if it's not attractive, how can the government enforce the people to actually do it? Okay, so in order to conclude, I'll just, write down or highlight the issue that when it comes to hydrogen utilization, especially for climate change mitigation, it's still, I would say, quote unquote, under development. And it's a big challenge in setting up an appropriate model if we don't really know what the actual product is. So from consumers' perspective, how are we going to do an analysis, a consumer's analysis, if we don't actually have an idea what the product actually is? And sometimes I've heard this many times, doing something however small is better than doing nothing at all. Well, it can be wasting resources. So I don't know about you, but I don't want to waste resources. It's irrational. Okay, if the cost of doing it is greater than benefit, you shouldn't be doing it. At least that's from the economics perspective. Of course, there are other factors as well, not just economics, that would probably make things, okay, it's fine to lose money, to burn money in order to achieve such goal. So lastly, should any economy pursue hydrogen? This is the big question, because me as an economist, without proper analysis, economic analysis of the, or should I say the cost and benefit analysis of hydrogen economy, my answer is I don't know. But of course, the current situation when it comes to climate change, there's a lot of issue about it. So if this is the only solution, then obviously, then yes, every country should pursue hydrogen. Thank you very much. That's pretty much it for my presentation. I'm welcome to hear questions.
Yes, thanks, Dr. Mohammed, for the very interesting presentation to give us an insight about the direction of current status of hydrogen economics from economic and societal point of view. So we have here maybe one or two questions to conclude this very interesting forum. A question here he's asking about Mr. Ahmed Al-Faraji is asking about what is your opinion about the hydrogen market structure? Is it better to be horizontally integrated, or it should be vertical?
So in terms of the current market, I would say the current market instead of the ideal condition, because there's a, how do we say this? So if it's a horizontally, or I should start with a vertically integrated. If it's vertically integrated market, obviously everything from upstream to downstream is being controlled by one firm or one entity or one institution. Right now, hydrogen is some sort of, the technology exists, but when it comes to the market, especially not the market for industrial purposes, the market for the fuel cells. The market has not been established yet. So for this perspective, it might be better to actually have a vertically integrated market so that everything can be regulated, everything can be controlled easily, because you have the full control from A to Z. But later on, once we have a market that's already established, we probably want to stay away from vertically integrated market because it doesn't create competition. It doesn't provide incentive to be cost efficient for the hydrogen production sector, whether it's upstream, downstream, or midstream, you name it. It doesn't create that competition. So firms would actually want to reduce their costs because everything is regulated. So, so my answer would be, it depends on at what the status of hydrogen economy is, if there will be a hydrogen economy in the first place that focuses on the fuel cells.
Yeah, from Mohammed. So maybe some question from while the other presentations, other speakers were speaking, they were talking, someone, more than one, were talking about the social acceptance of hydrogen implementation and also policy. I don't know if we can have policies that can maybe force this acceptance, or yeah, what do you say about this situation?
Yeah, one of the the nuance of this problem was actually mentioned by Mr. Wolfgang about when it comes to a bus, the acceptance of using hydrogen for a bus is making sure that there is actually someone who operated. So well, in a way, I agree, but to a certain extent. But at the end of the day, you can have a bus operating with hydrogen, but if there's no one that actually wants to ride it, or maybe just a few, so that's not a lot of benefit out of it. So in that sense, the government can never actually enforce this, especially when it comes to consumer preference. It has been proven all over the time, all over the place. If there is some sort of, for example, just look at an example of vaccine. Hey, everybody have to be vaccinated from COVID-19, but let me ask you, do you know any country with 100% vaccination rate? Zero. And it has to be zero. There's no way for government, even if you implement such sort of policy, or we'll do this here, this way, that way, this way, that way. There will be, people who just don't want to get vaccinated. And the other way of solving this problem is not by, making sure that it has a good policy formulation to make sure that, or to enforce people in terms of their consumption. It's actually what Mr. Wolfgang mentioned. It's to raise awareness that, look, it's perfectly fine to actually, use this bus or hydrogen. It's perfectly fine to have, vaccinated but with this vaccine for COVID-19. But even with those, even with raising awareness, some people are just, how do we say this? How do I say it nicely?
Conspiracy theory, yeah.
Yeah, it's just the way it is. And one way is, instead of I should probably focus on, instead of looking at policy formulations, it's more towards making sure that the product itself is attractive. So there are different angles, different perspectives of how this can happen. And currently, the current research is just focusing on, we just have to make sure that the cost is as minimum as possible, and that's it. Which I think, it's kind of an incomplete picture.
Yeah. So with this, Dr. Mohammed, so we are closing our forum for tonight. So thank you, everybody. Still, we have tonight more than maybe a kind of 400 participants, and now at least to this late time, still we have over 200 audience. So thanks to everybody who have joined us in this very interesting forum. And hope to see you, inshallah, in our upcoming event under Hydrogen Interdisciplinary Research Center for Hydrogen and Energy Storage. So have a good night and see you, inshallah, very soon. Assalamu alaikum.